All right. Let's see. Hi, everyone. So I'm Patrick St-Amant. I'm the CTO of Zetane Systems. And yeah, so today we'll be presenting you about why seeing is believing and understanding. So we'll be navigating inside the complex neural networks with the goal to accelerate discovery and reduce the guesswork. So I guess, Mina, you can present.
Yep. Hi, I'm Mina Amiri. And just to introduce me, I did my PhD at McGill in biomedical engineering, and then I worked as a postdoc fellow at Concordia University in Montreal for 2 years. And in fall 2020, I joined Zetane as a data scientist. And I'm going to present after Patrick.
Thank you. So, all right, just a few people are getting in, so it's a good crowd. So, okay, so I'll be starting. So, we'll start for the first part. So, who Zetane is? So, Zetane and the team. So, this is us, and we're based in Montreal. We're a team of software developers, data scientists, simulation expert, and 3D rendering specialist. And so, what are our main focus are about opening the AI black box and to propel enterprise AI project. And when we say propel, is that we want people in companies to take the AI project and propel them. We saw that it was really difficult to start with the AI project in enterprise and move it along up to a product. So that's what we've been doing. We've been helping multiple companies to do this. And our software, we've released a free Zetane viewer. So this is a software to open up the black box of AI models. And we have a free viewer, so you can go to zetane.com. If you go in gallery, you'll see a lot of examples. So everything I'll be showing today, you can actually open on your own computer. So you just download the software and you'll be able to inspect neural networks. So when we talk about neural networks, of course, the word neuron in there, we know there's something related to the brain. That's kind of the idea behind this. So in a way, when it started for the microscope, telescope, and brain imaging technique, the first time people saw those pictures, there was not already a language to understand them, and people needed to develop their way how to look at those complex systems. So with time, there became doctors of brain imaging techniques or MRI, so they were able to look at those images and see pathologies. And so what we've created at Zetane is a way to open up neural networks, and so that you can quickly access the data, so that you're able to debug, optimize, and also build some trust related to your models. So what we're able to see is what is inside of the artificial brain. There's pretty surprising impacts to this. Is that when you open it, you start seeing like what you could fix, and this really reduces the time you have to spend before retraining and guessing again what should be the next step. And not only that, but because now you can see it, people around you start believing its power. So we saw that there's it's not just opening and debugging and optimizing, but it's also everyone around it will be able to get involved in the process of developing an AI project in enterprise. So this is what it looks like. I'll be showing this in detail in a few minutes, and yeah, so what we'll present today, so there'll be a few sections. So I'll be presenting for about 25 minutes. Mina will present for another period after, and we'll have time for questions at the end. So there's a few steps we'll be presenting of what is a project in enterprise, and also we'll jump into the software that will open the black box, and I'll try to explain like kind of to a good level so that everyone understands what's neural network, no matter what your background is. And after this, Mina will jump into like actual insights that were gained. So you'll basically be looking at MRI images of neural networks in a way. So our free Zetane viewer, which I mentioned earlier, it's supported on 3 platforms. The reason why it's free is that we want people to get to know what neural networks are, and also start optimizing the model and getting these insights into those models. And there are many insights to gain, and each insight is really valuable because it helps you make your solution better and faster. So there's a few things that we can open. So there's the model architecture. So in a certain way, you can see it as all the different parts of the brain, all the operators. So there's many components in there. There's also so what we do is we support computer vision models, deep learning models, and also we support NLP, so which is a language related to language. And so we're kind of agnostic to the type of model we support, but we really have a lot of examples related to computer vision. So in our gallery, you have Zetane files, which is models that we created. We created the script. We created a file for it for you to load and not have to worry about Python code and so on. So you can really jump into it and inspect them. There's another type of file that we support. They're called Onyx, and they're pre-trained models. And these are models that have been made by the community. There's a really large community supporting the Onyx standard. So this standard is the Open Neural Network Exchange format, and the objective is to have an exchange format that you can use to go from one framework to another. And there are many frameworks, for example, PyTorch, TensorFlow, Keras, and so on. So the idea is to have an open standard for machine learning interoperability. And these are the members of the consortium, and we're also part of this. So you have like ARM, AWS, Baidu, NVIDIA, Sony, Microsoft, and IBM, and so on. So it's a pretty big group, and it's moving really fast as a standard. And yeah. So the question is, so AI and ML projects in enterprise. So maybe I'll describe a little bit what kind of certain parts of how it evolves. Usually it starts with a business opportunity, and a business opportunity, it's a place where AI would have a good application. And this varies between different enterprise, and we see enterprise in aerospace and constructions and in the manufacturing and in forestry and so on. So, but each of them have a certain place where it's best to start. We have helped people figure out where to start in those enterprise, but also there's always kind of a few champion in the enterprise, people who know their topic really well. They're the subject domain expert. They do this all day long, and because of that, they are able to see where AI could be applied. And our job on that part is tell them, okay, yes, that would work. Oh, this I'm not sure, and then you kind of guide them to get to this business opportunity. Usually there's a few things you need. You need good data related to this, and I'll explain later what good data mean. It's not necessarily a lot of data. It means a certain thing, and I'll define it. And also what it needs to do is kind of be better than human. If you replace that piece in the business by a AI model, then you want it to be really give some advantages, so there's some return on investment. So also there's in an AI project in an enterprise, there's a lot of people involved, both vertically and horizontally. So there'll be colleagues, like one VP to another, and then there'll be like say a developer to a supervisor, R&D directors, and so on. So it goes both sides. So it's a team sport, but not only a team sport, it's a team sport with coaches and general managers. So being able to understand what's happening in AI models is important. So for data, I mean, you probably heard, yes, machine learning needs a lot of data. And it is kind of true for some models, but also with good data that is not necessarily it depends, because sometimes you need a lot of for a certain type of model you need a lot of data, but for others there's really good techniques that will do the job. So quantity is good. I would say the right quantity for depending on your application. And there's different type of data: tabular, time series, images, videos, and text data, textual data. So that would be like different text that is used within the enterprise for natural language processing. Also, what you need is that the data is of a good quality. You need to figure out if it has been annotated or not, if there's a human somewhere that labeled the data, if it's needed. And something that is usually forgotten is how easy it is to access the data. And this is something that is probably one of the most important questions related to how long the project will take. Because if you don't have the data, there's really no AI application. So data is the key here. When you have it, there's many opportunities. So the idea is to figure out if the data is easy to access. And this can range from different, there's different types of things that can block that. Is it confidential data? Who owns the data? Is it the client or the client of the client? How will they get it? Who will be involved in getting it? And what is the type of database and the format of the data? So there's a lot of question, but when you have the data, there's a lot that can be done. So it's about getting the right data, and then you'll be able to have a pretty powerful AI solution. And never forget to ask how long it will take to take the data, because project needs to otherwise they take longer to go through the process. And the people involved, and that's just the beginning of the list. There's someone that's tech-oriented, software developers, data scientists. Usually here, those are they'll be your champion. They're the people kind of leading the project by their passion. And then there'll be like the managers that will support them, and everyone needs to understand what AI is about. And that's a very important part. And that's where we also have a very, we saw that the visuals that we offer gave a lot of leverage to actually move those projects in enterprise. Otherwise, if it's just a data scientist that has a good idea, it needs to be communicated, the benefit needs to be shown, and also the solution, which is an AI solution, needs to be understood. And ultimately, it's about understanding what AI is and what machine learning is. And if all these actors have a good understanding of what it is, what it can do, then there'll be a lot of trust in that solution. And this makes the project kind of flourish really quickly. So the question is, but what is AI for most people? So it will be something like that. It's something magical that is futuristic and so on. This kind of those images that we see on websites, like the future of AI and so on, it does give that sense, like, oh yes, my business should profit from these amazing like AI techniques. But the reality is a little bit different. It's that. So it's kind of code, pretty dense code, and when this code runs, you end up with a few metrics, bunch of data, and you can present in different ways, but ultimately it will end up being a small graph. And usually what you have to rely on is the output, but if it's not a computer vision, it's not necessarily, you won't be even able to show this. And and even when you show this, like, the question is like, how did it choose it was a bicycle? How did it choose it was a dog? And there's even, this was a good labeling, but those are usually just the one you see on the website saying like a computer vision, but there's a lot of them that it sees a car as a carrot or things like that. So these are outliers, and when you're a domain expert and you see that the car has been labeled as a carrot, you start to wonder about the strength of the algorithm. So you need to make sure that it needs to be improved to the place where even the domain experts saying like, yes, that's something I would even see myself at that speed. I see the advantage. I see the labeling is right. So maybe I'll do a little demo of what our tool is, because where we stand is a little bit in between these two. So between this and those code. And because we're able to take this model here and open it up and be able to see all the data inside, you'll see that it gives a lot of understanding. And I'll take the time also to explain what a neural network is also. So this is our user interface, and it's a 3D space. And we have provided a few snapshots that you can also use. I'll take maybe the basic one, which is MNIST, which is the classification of written numbers. So we see a 4 that's been written by a human, and that's the image that the neural network is getting as an input. And the job of the neural network is to go through each of those operations, and each time there's a small transformation happening to the data. And in the end, as it goes through the network from left to right, at the end you end up with a certain solution, which is a number between 1 and 10, well, between 0 and 9. And when you have classified this number, so the neural network will classify this number. So this is a classifier. It takes a written by n, a number written by n, and it classifies it. So that's nice. So you can see sometimes you get 97% accuracy. Maybe I think it's much higher now. It's like you can get 99% accuracy for classification of those numbers. But what does it do? So what it does is it passes through all these nodes, and you're able to actually look at every aspect of the neural network. So in this case, you're seeing what is the first layer seeing. So it starts to compare the numbers. And in this case, when you look at the colors, it means that the color is really, really high. When it's the more red it is, the higher the value. So this one would tell you that, okay, it's really seeing the background and it's focusing on the background. This one is focusing on the internal values of the 4, of the pencil stroke. And there's different things that look. So you have another one that looks a little bit more at the background. And the more you go, you can see what is happening to the focus. Where is the network putting its attention? So we really have this aspect that the network is evolving and starting to classify these things. And every time you have a transformation. And these are, yes, they are images, but ultimately what they are these types of objects. So I'll maximize this. So it's a tensor, and these tensors are multi-dimensional object. In this case, it's a 3-dimensional object. So if you go there, you can see all the structure of the information. So this is exactly as it is. This is what the neural network is seeing. And there's maybe I'll show a few other things. So what it's saying, and when you look down to what it is also, you'll see that it's made of numbers, and it's a little bit more. It's made of all these numbers. This is what the neural network is seeing, but we attribute colors so that it's easier to understand. So this is just an overview of what a neural network is. If you didn't know what it was, I hope it helped learn more about it. So I'll go back to my slide here. So Mina will be presenting you a neural network called UNet, which is related to image segmentation. She'll go in more detail about it. So this we've seen, I mean, it's we really access all the components. So when we say we open the black box, we open absolutely everything of the black box. Everything is accessible. There's nothing left behind, so we can really view everything. And there's something that I haven't maybe insisted on, but whenever you click on one of those tensors, you're able to see the distribution of the values. And this would be worth it to be a little bit more precise on this one, because Mina will be presenting on this. So I'll take one of them. And if I click here, you see here there's a distribution of values, and this allows you to know how these values have been distributed. So it tells you like what's the lowest of all these values, what is the lowest value, which one's the highest, and where most of them falls. So it gives you a curve, and this curve is really important and helps you make a really important decision about the neural network. So we can do satellite imagery. There's different types of model, and in different domain of applications. So the way we work is usually what we realize is that there needs to be a lot of exchange between many actors, even on the when it's horizontal and with one or two level up. You need to get people's input into those models. So what we do is that someone creates the model with a Python script. You use an advanced model, and then after this, a file is created, which is the .zetane file. And from there, we usually send that file to each other so that we can actually give inputs to it. So this way, we're able to look, okay, what's happening in the network? Is everything working correctly? And then we write a few comments, and then we tell, okay, so maybe we can fix this. It seems like at this layer, this seems to be like no more signal passing in the brain, the artificial brain. So this helps us really improve the models quickly. We'll be presenting a case where a state-of-the-art model was improved in an afternoon, which is kind of something really difficult to do. Usually the way models are built, so now that you have your business case, you have a data scientist working on the topic, and you have the approval of everyone, models needs to be trained. And then the way it happens is you start looking at the numerical values and trying to get the best thing. A few of those numbers needs to be really good. And when you're happy with the numbers, usually you're not necessarily happy right away, and you'll never be happy the second you start, you'll never be happy with the numbers you see. And then what you try to do is you have some intuition, start guessing, and sometimes you just say, you know what, I just have to live with those numbers, say 80% accuracy, because that's the nature of this problem, and you'll decide you'll do nothing. So you won't know that there's really impressive things to do, that your approach was probably really good. So, and then you go to adjust the model. So what we do is that we go differently about it. So we train the model is trained, the model is designed, then the model is trained, and then it's a matter of looking at the metrics, but also look at the inputs, the data input, looking at the model, its structure, and also how it processes the internal data. And the internal data is the key. Basically, it's how the network works, and this tells you a lot. And from there, it gives you like insights that are much deeper, and it gives you decisive strategies of how to improve it. So it's not about there's the model, there's the data, these are separate, but it's about the combination of both of them. It's really an interaction between both the data and the model. That's the importance in neural networks. And yeah, and it helps you. You can even stop training early. And when we say training, that means the model is running on a very expensive machine in the cloud, and it costs a lot. It adds up those costs. And also during that time, you have to wait and wait and wait, and it's you need to improve this. So if you have a decisive strategy by looking what was wrong with the model, which Mina will demonstrate a use case, then you improve by a factor at least of 10. And also it helps you increase the trust and the safety about the model, and also engage with everyone around it. So that's the value of being able to open up the models. There's another aspect is to be able to engage the operators, the clients, and the stakeholders. What we saw, what really worked is that when there's a nice dashboard that both includes the model, but also all the analytics and the inputs and different the machines running it. And these dashboard gives a lot of trust, because not only you see those numbers that you can maybe in real time, but you're seeing, say, the prediction move in real time, but also you're seeing the model doing its work. So the combination of both the model and the data for an operator is valuable, because it brings you trust. You don't necessarily have to always look at the model, but you go into it when you think there's something here that you're not sure that it's happening correctly. If it's not happening correctly and you have some knowledge of your model because you work with it all day, then you can go look, how is it seeing that data? So you can build a command and control, and this is more in the philosophy of Industry 4.0, where you have this advanced system that presents the data as it is. And as it is means that if it's a 3D environment, if you're monitoring a 3D world, then it should be in 3D. So in our case, we put a lot of emphasis on being also a three-dimensional, a 3D engine. so that we can really present the data as it is and not just a projection of it in graphs, but really present, okay, so this is a scan of the whole building of the construction site at this moment. So maybe I'll talk about a use case. So this was for an autonomous train, and we needed to demonstrate that the train would stop when it sees an obstacle on the tracks. We had like a 3D rendering of this, and we had ways to look at it. And I can maybe present the video just after this. And what it was doing is that you wanted the train to stop when it sees something in the tracks. In this case, the test image was something almost ridiculous, the biggest boulder there ever was. And it turns out that it was good that the train was stopping at the boulder. But when you started looking into the network, there was a layer, and you can see blue means nothing's passing. All these things are not being seen, they're not passing. The only thing that the model was really seeing to make its decision is this little circle here. And so it was stopping, but it turns out it wasn't stopping because of the boulder, although for us it seems super obvious, but it was stopping because of the tunnel. So the reason is that the model haven't been trained to be recognizing tunnels as non-obstacles. So this was that was a good catch, because without seeing to it, we would have never known that that's what the model is seeing, because this is the explanation of what it's seeing. And so the decision why it's seeing this is why it's stopping is because of the tunnel. So that gave us a really good use case for that. And also you have we can also do geospatial data, and that helps us engage with different other types of data. And this is something that we decide to integrate, because it's they're called XAI libraries, and there's many of them, and they allow you to look at where the attention of the model is giving its energy and where it's looking. And sometimes it tells you like, okay, so for deciding this is a king snake, it's really because of this structure. And each of these models will tell you different things. Those are coming from XAI libraries. And so there we have the free viewer, and that helps you. But there's also ways to really get into the Python workflow. I don't want to go too deep in there, but it's just a few lines where you send your model to be presented in Zetane. So this allows you to be in your code, Python code, as a developer, as a data scientist, and be able to present your model and debug it almost on the fly. And this can also be done in training. So this allows you to train a model, so in the cloud, and every epoch you kind of save the model or save the input, and this allows you to go inspect back, kind of do forensic of what happened during training at each moment. So this allows you to make those stop training early. And when we're saying stop training early, models can train for 24 hours. That means machines are running for 24 hours. So there's a lot of cost involved. So if you can stop after 2 hours and decide, you know what, I was not on a good path, so that really helps. So Mina will presenting many insights. So when we're looking in the network, now there's also there's a lot of new things to look at, and there's a lot of things to be discovered. So for example, what is the best distribution for a trained network? So here, like when the model is not trained, all the weights, basically those are the numbers that the neural networks remembers. These numbers, when they're initialized, they're all like this. They're all like kind of randomly initialized. But when you train them, the distribution becomes nicer and nicer. So we don't know which one yet, because different models will have different types of distribution, and this changes with the model. So these are important things to look at. And yeah, and I'll let Mina kind of jump into it. And you'll basically be diving into the neural networks, I guess the artificial brain. So yeah, Mina.
Yeah. Hi. Okay. Yeah, so I'm going to present some use cases of how to use visualization of internal tensors to improve our models. And these use cases are mostly on image segmentation, on medical image segmentation and satellite image segmentation. And I thought maybe it would be good to talk about segmentation very short. So in segmentation, the goal is to assign a label to each individual pixel, and it's a difficult task because we need to have a label for each pixel. It's not like object detection that we group some pixels in one object. So we need to have a label for each pixel, and there are different types of segmentation. The one that I'm going to talk mostly in this presentation is called semantic segmentation, when we don't care about different objects of one type. So for example, in this image, you can see that we classified all the people as one group and the background as another group. So we have only two groups. There is another type called instance segmentation, when we care about different objects. So in this case, we have 5 different labels for 5 people, and we have another label for the background. So in this case, we have 6 labels. And to evaluate segmentation, there are different metrics used to evaluate segmentation. The easiest one is to calculate the pixel accuracy, just to count how many pixels are classified correctly. But we have also Jaccard index and DICE index. They are very similar, but and they differ very slightly. So if I don't go into the details, but if we consider the ground truth mask as A, ground truth mask is the mask that we are looking for. And if the output of the model, we call it B, or the segmented mask, if we call it B, Jaccard index is the intersection over union, and this is the equation. And the DICE index is very similar to the Jaccard index, but a little different. And as you can see, if A and B are equal, then both Jaccard and DICE will be 1. And if they don't have any overlap, meaning that the segmentation is not working well, then both indexes will be 0. In this presentation, I'm mainly talking about DICE index. So the DICE is between 0 and 1, as I mentioned, and 0 is the nothing is detected correctly, and 1 is the perfect segmentation. So I categorize the visualization aspects into 3 groups: data, network architecture, and internal tensor inspection. And I'm going to go into more details about them. So as you all know, in deep learning, data is super important. We need to have the correct data to train the network. And the network learns what we give to him. And so it's really important to have the correct data for training. And we need to make sure that the shape of the data is correct. We need to make sure that the pre-processing and the normalization is correct. And we are feeding the network with the correct data. So this is just one example of what we had in one of the projects. We were trying to segment the lungs from X-ray images, and it's a quite easy task. So we were able to segment the lungs quite easily, and we were actually happy with our results because we had the state-of-the-art results. But then we were just curious to see what's going on inside the network, and after visualizing the internal tensors, we realized that the network is paying much attention to this corner at the top of the image, and you can see in different layers, in different kernels, that the network has a great attention to this part. And when we looked at the image, we realized that it's because of this white tag at the top of the image, which was used to anonymize the patient data. And we had the same issue with all of the images in the data set. So we decided to clean the data and remove this white tag and retrain the network to see whether we can improve the performance. And here are the results. At first, the average dice score was around 0.97, which shows a good segmentation. And then we cleaned the data, we removed that white tag, and we retrained the network, and we could improve the dice by 1%. And it may seem not a big number, but because this was the state of the art, we could improve the results by around 1%. And this is another example when we were trying to segment the COVID-19 lesions in the CT scan of the patients. And the data we had was some medical data format data, and there was some headers with all the information about the coordination and voxel size and all the transformation parameters of the data. So we didn't have a good performance in the network, and we didn't know why. But then when we visualized the network and the data, we realized that the data that we are feeding to the network is not the correct data. This is what the network was seeing, and this is the correct data. So we couldn't realize this problem, because when we tried to plot the images and slices in the Python, because of the information in the header, the data was shown correctly in Python because it had access to the header data. But when we used the data for training, it wasn't correct. So we needed to convert the data to a standard format and then do the pre-processing to make sure that the data is correct. The second aspect is the network architecture. So when we are implementing a network and when we are developing a neural network, we want to make sure that all the layers are connected correctly and in the way that we look for. And we usually, like when we are coding, we copy and paste one layer, and we usually forget to change all the parameters and all the inputs. And when we have like more complex networks with skip connections, with different batch normalization and concatenation and different activation functions, we need to make sure we have put them in a correct order and in a correct place. So this is one example of a unit in the Zetane engine. You can see the U shape easily and all the connections from the encoding and decoding parts. And if we zoom more, we can see the more connections and see the connections in more details between different layers. We can see the activation functions for each layer, and we can see the concatenation and batch normalization used for each layer to make sure that the network structure is as what we wanted. And if we zoom more, we can have access to all the weights and kernels of each layer. We can have access to the histogram of all the tensors, and we can have access to the feature maps of each layer. And here is another example of how we use visualization to make sure that the network architecture is correct. The usual way would be like to draw the model on a piece of paper and try to implement it step by step. But by using the Zetane engine and visualization, we are able to see all these structures very easily and fast, and we can have more confidence in design and implementation of neural networks. And the last aspect, and I think the most interesting aspect, is the internal tensor inspection. If we can have access to the feature maps, all the filters and biases and inputs and outputs of all the layers, and the statistical properties of the tensors, such as the parameter range, the histogram, the shape, the minimum and maximum. That would be great to analyze all these tensors and to get insights how to improve the network. This is one example. We were trying to segment some COVID lesions in the CT images from the lung of the patients, and the network was almost good, but not as good as we wanted. So we inspect all the tensors, and we realized that this branch of the network doesn't see anything. All the feature maps are zero. Actually, the signal doesn't pass this branch, and the usual way would be like to write some code to understand what's going on inside the network, or we didn't realize it at all. But by visualization, we could easily see that this branch is useless in the network. So what we did, we add batch normalization to each layer, and then we could have the signal passing through this layer, and we could improve the results. The other option would be to use another activation function, such as leaky ReLU instead of ReLU. And this is another example of a weak segmentation we had for breast ultrasound data. We were trying to segment the tumors in the breast ultrasound data, but we didn't have good results in some patients. The usual way would be to analyze the errors and try to find why the network is not working well in some patients. But the visual way, we noticed that the histogram of the last layer, the tensors of the last layer, when we have a good result, the histogram is so steep. But when we have like bad results, the histogram is more broad. So the top is 2 examples of good segmentation, and the below is the 2 examples of bad segmentations. And as you can see, the histograms are totally different. So based on this observation, we were able to develop an adaptive thresholding method, and we could improve the dice score segmentation in the images with bad segmentation. So this is just one example of one of the images with poor segmentation. This is the ground truth, and the tumor is shown in yellow, and this is the old network and the old thresholding, and the dice was 0.74, and after using adaptive thresholding, we could increase the dice to 0.82. And this is the last example I'm going to present. It's on segmentation of satellite images. We had a network to segment the satellite images into different groups, like the trees, the houses, the streets. The network was working fine, but we wanted to improve the results. And so the usual way would be like to use a more complex model, probably, or to use more training data, or to try to search for more for a better hyperparameter. But with the visualization, we just inspect the tensors inside the network, and we realized that just the first layer, it doesn't pass the signal correctly. After the first layer, we lost most of the data. So what we did, we added batch normalization before the activation function. So before it was after the activation function, but we switched the place, and we had the batch normalization before the activation function, and so now we could see that we have the signal passing through the first layer and go on. And by this change, we could improve the total accuracy from 88.31 to 90.75, like more than 2%. We could improve the segmentation accuracy. That was great. And yeah, there were some examples that I presented to you how we can improve the models and the performance of the neural networks by visualizing inside the networks. And thank you very much for your attention. And I think, and now it's the time for questions. If you have any questions, we'll be happy to answer.
Yeah, hi. Okay, so we have our first question by Jalen. In which workplace, in which workplace can these segmentation designs be implemented to improve work efficiency? Mina, did you want to take that one or?
Yeah, sure. So if I understand the question correctly, I use like both TensorFlow and Keras and PyTorch for implementation of the networks, and you can have access to some of these visualizations using like coding to see that inside the networks, but all of these images that I showed, they were inside the Zetane engine. So we have access to all of these layers and all the tensors, and based on what we observed, we could improve the results.
Okay, so there's another question by Lillian. The different layers of the network have varying dimensions. How do you map their activations to the original image? So maybe I'll just describe the network a little bit more, and then Mina, you can jump in. So the network is made really of two things. So it's a series of operators. So some more like matrix operators, and so each node is an operator. And in neural network, there's the other component are tensors. So you can think of them as matrices or tables of numbers, multidimensional. So they're multidimensional matrices, and there's nothing else in the network. So when you send an input, you're sending this matrix, which in this case it's an image, has a certain dimension. Then the operator will take that tensors of a certain dimension, and it will transform it into something of another dimension. Sometimes it reduces its height and width and so on, and it passes through. And those tensors, you can see them as boxes, and they change shape and change colors, and the colors are basically linked to the numbers. So when you send an image to a network, it's a series of numbers, which are the values for your pixels. Usually normalize them, and then it changes. So the way when we get in the middle of the network and we open a tensor, this is the result of after the initial image has passed through all the other operations. So it's been multiplied by 2, it's been averaged and so on, compressed, and then you see that middle image. So that's I can explain. So the mapping is done by the network itself, and it's really just a transformation of that image as it goes through. Hope the question helps. I hope the answer helped, and if you want more, I can say more if you send another question. Mina, can you read the other question?
Yeah. Just I wanted to add that, as Patrick said, in the middle of the network, the size of the feature maps is different from the size of the original image. But you can inspect the abnormalities, and you can like do research and understand what's wrong if you see any abnormality in the middle of the network, and how to change your network, or how you change your data to resolve that issue. And the next question is from Pablo. How do you plan to use new hardware and software technologies to improve the neural technologies further within the near future?
Yeah.
I guess, Patrick.
So in our case, what we do is that we stay really close to the normally used frameworks. So at this moment in time, it's like I would say it's Keras in industries, and so we stay really close to that, and Onyx, which is another player in the field. So what we do is we're not trying to kind of create a new framework. We're just basically taking like a very used framework, which is things developed by Google, Facebook, and so on. And what we do is we take this data and project it in our space so that we can interact with it and also manipulate it. So this is where we're seeing is that we follow what is the main technology, and we make sure that things are visualized and or it can be interacted with. And so this is how we're evolving so that we can always give those, be able to give all these really strong insights. And not only this, but like all the insights that Mina presented, each of those insights can be automated. So this means that instead of having the expertise of Mina saying, okay, there's something happening with those neurons, these things can be identified automatically. So it's a one button, and then you basically know where, say, your standard deviation is very low, or there's certain things happening. So all these can be identified, and it helps you automatically to look at the right place in the model. Okay, so there's another question. From Ivan, I understand your solution has been developed for imaging and NLP. Any plan to address time series neural network analysis? Yeah, so for sure, I didn't mention it, but this I would say we support already. Because time series, when like I'm describing a table, is basically a matrix of all these numbers, and it passes through the network and becomes tensor. So what happens is that you will basically get still access to how it's transforming the network. So we do time series all the time for business clients. It's actually very useful, and especially when you're in the world of deep learning. The difference with these, because for these you won't get images to analyze, so you really have to rely on the distributions of the values, and this becomes really useful, and quickly you can inspect what's happening with the signal. Personally, I always start going to look at ReLU, because that's the place where the most of the stuff will stop passing from there, and then you can start looking at how much is passing. You can look at the range of the distribution, and for time series, usually one of the other data scientists, what he does is like he does a pretty crude draft. He prepares the data, does a crude draft of the model, runs it once, and then he launches it in Zetane, and then he's able to right away go back and apply a very kind of strange techniques related to normalization. So maybe Mina, if you have more to say on this.
No, I don't have anything to add.
Okay.
Thank you.
Following Lillian's question, so the examples you showed with original images color-coded is thus only from layers with the same dimension as the original image. Yeah, no, they have different dimensions. So the image that we're seeing is not the same dimension, especially if there was a pooling and so on, so the image probably shrank a little bit, and it really depends. It can actually, if we go later in the network, it even becomes like a long vector. So all these kind of becomes like a extremely compressed. So the image that you'll be seeing at a certain part, it's maybe it's the image sometimes shrank a little bit, and so basically you have don't have the same mapping, but the way convolutional neural network works is that they keep looking, say for example, it starts looking at the corner, and then when you go further in the network, the way why they're really good is that it keeps that information about the corner of the image at the same place within the network. So it doesn't shift the image around, and that's kind of the strength with convolutional neural network, is that it really looks locally at the data around it, and then it keeps it stable along the network, and that's why we're able to see the same image as it goes. If we're looking for things like time series and fully connected layers, all the data passes in many directions, and it becomes harder to follow. So that's why you have to look at distribution.
Yeah, I just wanted to add, like you're right, like the first layers of the network, we can see the overall structure of the image, but as we go in deeper, we don't see the image anymore. We just see some features that are extracted from the network, and like I showed some examples in when I was talking about the batch normalization. If you remember, they are not showing the original image anymore. They are just some features that we cannot understand what they are, but the network can understand. So I showed both examples of like the features from the beginning of the network and also from the deep layers of the network.
Thanks. So next question by Andreas. Do you upstream activation from deeper activation level to higher and can map it to the raw image data? I would say yes, but these are what we do is we use different libraries related to XAI, and these libraries will basically what we're working with is the forward pass, and these was how the data was processed through the network. But when you're training, there's also a backward pass where all the weights are being updated going back through the network. And these also have a lot of values because but those are related to when you're in training. When you have your pre-trained model, what you want to see is how it passes through. But in training, you want to see how everything goes up again. So then you can look at the gradients, which are all the changes happening in the weights. This can be done through different libraries, and I would say, yeah. So the idea is we use the library, and then you're able to see how it changed up to the beginning. And there's other techniques related to that. Maybe, and I think also your question probably has another thing. Is it possible to take the final value and bring it back to the beginning, kind of invert the old network? I would say it's possible, but it would probably be done by code because you need to invert all the operators. If you have the inverse of all those operators, you'll be able to bring it back. So it's a little bit more tricky in that case. The way it's done is usually you're looking for an answer and you do perturbation at the beginning, and then you can see what will map to these, and these are related to XAI techniques. And, I think there's a, oh, I just got that. Okay, so there's no time for other questions, so I was really happy to present to you today. If you want to try it out, and you can go to the website zetane.com and you go to the gallery and you'll be able to download. It's free, and feel free to reach to me on LinkedIn, and I'd be happy to accept your invitation. And if you want to talk further, I mean, we support also many clients in their AI adventures, I would say. And what really helps is because we basically are special. The Zetane way is really visual, so that you really have this way to bring this within your enterprise and your clients. So not only we have those tools, but also we help people like develop their everything within their company. And it's a lot of it's challenging for people in enterprise from what we've seen, but we now have a very good experience with really large clients to actually bring those projects up. Even if there's a data scientist within the enterprise, there's so that the project doesn't evolve, it needs proper ways to do so. So happy to talk. Feel free to reach out to us. Thanks for watching, and really nice questions. Thank you.
Thank you.